Hi, so let's go over a bit more on the Green's theorem. So let's do some examples. So maybe first let me write down the Green's theorem. So the idea is that you have, or if you have some region, let me call the region D, and you have its boundary is this path C, right? Sometimes this is written, you might see this as sort of this almost like this partial differential operator, but it's this curly D of D, right? Is just saying is the boundary, right? This means boundary. Sometimes it's also written as B. Right? You might see that, but this is fairly common. Anyway, so if I have a path going around a region, and I have these these two functions P and Q, so I write down the integral around C of P dx plus Q dy, then this is equal to the integral over the inside of dq dx minus dp dy with respect to the area. Alright? So that's Green's theorem. Right? Now, it's actually what's maybe a little different from, this is, as we saw last time, it's really just fundamental theorem of calculus, just in sort of more complicated guys, right? It looks a bit more complicated, but underneath it's really just fundamental theorem of calculus. It's integrating over the inside, some sort of a derivative is the same thing as integrating. Well, here this sometimes it's called a one form, P dx plus Q dy over the boundary. Right, so it's so how this is used? Well, quite it can be used both directions, right? If you have something that looks like this, you figure out some Q and P, and we'll see an example of that as well. Then you could write this as this, and then compute the path integral. This would be more like how you are applying fundamental theorems of calculus generally in Calc 1. Generally, you wanted to solve what's inside, so some integral by figuring out the antiderivative and then evaluating it on the boundary, right? And generally, you don't do it the opposite direction. Although that can also sometimes that's useful, but most of the time you use it in reverse. Well, here it's sort of the other way around. A lot of at least the simple applications of Green's theorem are starting with something like this and writing it like something, something like this. It's just, you're basically, it says that these two things are equal. So, if you find one and the other one is simple to compute, then you do it, right? Okay, so let's do an example over. Let's do unit square, right? So it's not quite a square, but it's supposed to be a square. Can't count to 3. Anyway, so this is my C, and this is the D is the inside over here, right? And we're trying to let's integrate. Let's integrate over C x plus y dx plus y squared dy. Well, let's first do it, and we've seen this kind of integral last time. Let's first actually write it down as the integral over these bits, right? And it has this is sort of an advantage over here. The dy is 0 over here. Here the dx is 0 over here. The dy is 0 over here. The dx is 0. So we can write this, sort of. Let me call this star, and then I'll say star is equal to. Well, let's write it down as this. Write down these kind of integrals, right? So it's 0 to 1 in terms of dx, so we're parameterizing with respect to x. So it's x plus 0, right? Because y is 0 on this bit, right? Dx, then 0 to 1. This is going to be with respect to dy, right? Now over here, x is 1, but hey, there's only y squared. So we just have y squared. Plus over here, we're going from 1 to 0 in terms of x. So it's just dx, right? Dy is 0 on this bit, right? Y is not changing. And here we have x plus 1. And then over here, we'd have 1 to 0 again, right? Now in terms of dy, it's just y squared dy. All right. Well, let's maybe I could just compute all these guys, but let's rewrite these a little bit, right? Without so it's just this, right? Let me leave this as is. Okay, over here I have a minus sign. Let's split it up into 2 bits. So I have minus 0 to 1, right? I flipped the order. And then that means I have minus 0 to 1 of 1 dx. And over here, if I flip the order, 0 to 1 y squared dy, right? Without having to compute these, I notice that this cancels this cancels this, so I just have, if I did all the arithmetic correctly, I have minus 1, right? Okay, not too bad, not too bad. Let's do it using Green's theorem. So using Green's theorem, this guy is the double integral over d of dq dx. That's 0, right? Minus dp dy 1. Hey, that's just that's equal to minus that's just minus the area of the unit circle. Unit square. I can't even tell a circle from a square. So it's minus 1. Okay, this was simple, but this was simpler. And that's actually, a lot of times what happens when it's one of the reasons why this is applied like this is that first, you over here you see that we've to write down something like a square, you have to write it as 4 integrals. So you're already doing 4 integrals. But the other thing is that when you take these derivatives, as long as you have functions, a lot of times it's if you have polynomials and if they have some bits that are, say, in the dy, there's only something in terms of y, and when you take the x derivative of q, it just disappears, right? Same thing if you have something in terms of x in the p. If you have polynomials, sorry about the time. I have to turn this off. Okay. There. Sorry about that. So, where was I? Where was I? Oh yeah. So, not only, so that's if I have if So for example, if P has some terms that are just in Y, or if Q has terms that are just in X, they just disappear, right? So this might make it simpler. The other thing is, if these are polynomials, then maybe differentiating actually makes things simpler. All right. So, so that's actually what happened here, right? I had this thing disappeared and this X disappeared, and Y became 1, right? So, and it was minus, so I got a -1, right? So it was, it became sufficiently simpler, right? Although, you know, this wasn't bad, right? Well, let's do another one similar to this. So if we have, so let's suppose the D is still the unit square. C is the path around it, and let's use this thing that I scribbled on my notes. So let's do the integral over C, and this is going to be e to the x, you know, to the x squared, right? So this is all in the exponent, plus xy dx, then plus we're going to have sine of y squared plus x squared dy. All right. So let's call that star, and let's do star in, again, 2 different ways. Well, or at least let's attempt to do it in 2 different ways. So first, same as before. 0 to 1. So this word y is 0, so it's just this guy. E to the x, y is 0, right? So hey, that's good. It's this guy. Plus right. So then this, you know, this guy. So it's 0 to 1. Then we just have to y, right? So this is when x is 1. So it's sine of y squared plus 1 dy plus 0 1 0, sorry, 1 0. It's not a nice 1. I'm not gonna be able to read that afterwards. Well, I guess. All right. That's the dx. So we have x squared, and here y was 1, so plus x dx plus now the last one is the 1 to 0. Now just the y1 sine y squared plus so sorry, x is 0, so this guy's not there, dy. All right, now this is still doable, but you have to be a little smart about it. You have to do exactly what we did before. You don't want to compute this. You can't compute it. But over here, you'll find that this is you know, this is really being subtracted. So this whole thing, you know, this subtracts this, and this, you know, this and this subtract, right? So if you know, once all the smoke clears, you'll find that this is the integral of 0 to 1 of 1 dy. Minus the integral of 0 to 1 of x dx, right? So this is 1 minus a half, so this is a half, if I'm doing that in my head correctly. All right, still doable, but you know, but it's getting more complicated. But let's use Green's term, right? d, and now we have, this is p, this is q, right? So dq dx, this disappears. This is just 2x, right? And over here, this so this is, I have minus dp dy x, right? DA, so this is really t. 2x minus x is just x dA, right? So I can write it as an iterated integral. Well, maybe let's even do the y first. Why is it still beeping? I thought I killed that window. Let me kill that browser completely. It's just annoying. Okay. Where was I? Try to refocus. Maybe I can do a better, slightly better focus. So if we have, I can do the y first, and then the x, because then I could pull out the dy, right? It's just an integral of 1, right? Well, or just integrating a constant, integrating x, right? So it's just the integral of 0 to 1 x dx, and I know that's a half, right? This is way easier, right, than this. Still both were doable. So let's maybe try a more complicated thing. So what if we had this triangle? Let's suppose this was the D and this was the C, and let's suppose it's the same, same e to the x, and it's just 1, again 1, right? X squared plus xy dx plus sine of y squared plus x squared dy, right? This is my integral. So let's first try to do it as a path integral, right? Again, the whole point of doing these in two different ways is to show that we really are getting the same thing, right? If you're just trying to compute this, you could compute it either way, right? So on an exam or something, if it asks you to use Green's theorem, then you'd better use it, not compute it like this. But if you just ask to compute it, you can compute it either way, if you can, right? If it's possible. Because sometimes, one of them is not possible to do, analytically, right? Over here, well, we had to resort to some tricks. So over here, let's do. So let's write this down. It's the first two bits are the same, and then we have plus 0, 1 sine of y squared plus 1, right? Dy. But now this one we have to parameterize, and we could maybe parameterize by t. I could write this as 0 to 1, and I could have my my parameterization for this. Maybe let me where should I write it? Maybe I'll write it over here. So the parameterization r of t could be 1 minus t, right? Because that is is going to give me at t equals 0, it's going to give me 1, 1. At t equals 1, it's going to give me 0, and it's going to go on this line. It's just parameterizing this line. So I write that down. I have I'll need also the velocity here. The velocity is easy. It's minus 1, right? So I will have so let's write down this thing. So I have e to the 1 minus t squared plus 1 minus t times 1 minus t, so 1 minus t squared, right, times this whole thing times minus 1, right, from the dx, plus then sine of 1 minus t squared plus 1 minus t squared, the whole thing again times minus 1, running out of room, dt, right? Sorry about it. But you will notice that this is this is okay. I have these guys, I cannot compute them, but now this doesn't really let me subtract anything, right? It's so I have either 1 minus t squared, then and this is all gonna come. These are gonna come with a minus sign, and then I will have these guys are twice, so minus 2. That guy is not a problem. I could deal with that guy, and then I have a minus sign of 1 minus t squared. This whole thing dt. Yeah, it's you know, the only bit of these integrals, you know, I can't do this. I can't do this. I can't do this. I can't do this. I can do this plus 1 I can handle, and this bit I can handle, but the rest of it I can't handle. There's no way for me to do this, right? So you know, it was the same thing, but over this path, over the square, it was possible. Over this triangle, now I can't do it. But if I do, if I apply Green's theorem over this d, let me call them, you know, just so that you know, if I'm, you know, maybe this is the d1 and this is d2 and c2, right? So this is over c2, this is over d2, right? Just so that we have, this is c1 and this is d1, right? So we can differentiate them, right? So over d2, if I integrate, well, it's still the d dq dx is still 2x, right? Minus dpy is still x. So what's inside is still x, right? So I have the double integral over d2 of x dA. And now if we write it, and you know, this is one of those things that you've been writing down as iterated integrals, right? So let's do again dy dx. So dx is on the outside. X is going from 0 to 1, and so we're integrating like this, right? Vertically inside, and we're going from 0 to well, here on this this is where y is equal to x, right? So we're going up to x, right? So we're going up to x, and we're integrating x, right? So again, as far as this integral is concerned, right, this inside one, x is a constant, right? So this is you know, go over here. So I still have this outside integral, right? And this inside, well, it's integral from 0 to x of x with respect to y, right? So it's just x times x. All right, because the length of the interval is x, and we're integrating x, which is a constant as far as y is concerned, right? X is not changing when I'm computing this interval, right? Okay, and now this is simple. This is 1/3. All right. So here you have an example of something that's an integral of a you know, a path integral, which is impossible to do just in the brute force way. It's still true that this thing, whatever this thing is 1/3, right? That's what it is. Right? Maybe there are some tricks that you can figure out to make this work, to do sort of the same thing as over here, but some more. Maybe do some. Oh yeah, we could probably do change of variables, and to figure out. Still, I mean, this is gonna be a nasty bit of work, but it's 1/3, right? So this is, using Green's term, it's almost trivial. Trying to do it like this is almost impossible. I think probably if you do the right change of variables here, I think it'll probably work out. But again, there's no reason to do that. It's so much simpler, right? So. And if you get something more complicated, it might turn out that it really isn't possible. Let's do something slightly different. So let's suppose that I have my D is the unit disk. So C is the unit circle, right? Right. So this is the unit circle, right? And let's suppose that sorry, I want to do single integral. Let's suppose that I want to integrate over C. I want to integrate minus y cubed dx plus x cubed dy. Now, this is it's not too bad to integrate, but let's do it. Let's do it using Green's term. So, because normally, you have to put in sines and cosines. You put in sine and cosine. You have to do. You could do it, but it's a little messy. It's much easier to do using Green's term. So, what is it using Green's term? It's the double integral over d of. Now, I have dq dx, right? 3x squared minus dp dy, which is minus 3y squared, right? This dA, right? So that's equal to, let me write it over here. So I have 3x squared plus y squared dA. Hey, that looks really, really familiar, right? This is basically this looks like something that I get with polar coordinates, right? It should be easier with polar coordinates, and this is a circle, right? So the thing to do is to maybe do the theta on the outside. It's a circle, so theta going from 0 to 2 pi, it's a unit circle. So r is going from 0 to 1. 3, this is r squared. So r squared, r dr d theta. Okay, so I have 0 to 2 pi, 0 to 1, 3r cubed dr d theta. The d theta is just going to multiply everything by 2 pi, but let me just keep it there. So over here, this is going to be, if you compute this is the antiderivative r to the 4th over 4, right? So, and I'm evaluating at 0 to 1, so this is 3/4, right? So 3/4 times 2 theta, 2 pi, sorry, pi times 3/4, so it's 3 pi over 2. Yay! Right, that was rather simple. Much easier than trying to put into sines and cosines. Let's do another example. Over the unit circle. Right. Again, the unit circle. And the unit disk, right? That's inside. Right? And now, just so that we have a an example going from the integrating over D back to C. Let's suppose that we want to integrate this thing, right? Now what we could do is we could write this in polar coordinates. It's going to be kind of messy, right? Again, it's doable. Nothing necessarily wrong with it. It's just going to be, it'll be, yeah. So, how about applying the Green's theorem in the opposite direction than we did so far? I mean, it's basically the two things are equal, right? So it basically says if you compute one, you compute the other. It doesn't matter which direction it goes, right? They're equal, right? They are the same number, right? So this is the same thing as computing this. Well, but now going one direction, if I know the P and the Q, it's easy to figure out what goes under the D integral. But if I know what's under the D integral, well, there's some choices that have to be made, right? I have to figure out what P and Q would give me this, right? Now over here, it's and you basically play around with this, and you sort of if you think about it, then what you could do, well, this thing, let's maybe have this be the dq dx. Why not? We can try. Well, the reason why really I'm doing, this looks sort of like a derivative. The y squared. The y squared is nice. So maybe this is the dp dy. Maybe I'm really sort of looking at this thing and say, well, so if this is dq, this is dp dy, this is the minus sign in between them, right? So I basically have to put the p in here, dx, plus the q in here, right? So I have to anti-differentiate, but these are polynomials; they're easy to differentiate. So I could start with the p. That would be y squared plus maybe something, right? Then over here, I can anti-differentiate, and I will get so this is x y squared plus x cubed, right? Now I look at this and I say, well, I mean, this thing, this is like x y squared plus x squared, right? That's nice. I'm on a circle, right? So polar coordinates. Think about it. Polar coordinates. Distance from the origin is x squared plus y squared. So it's nice to see this. Over here, I don't quite have that, but why don't I add an x squared in here? Why? Well, because I can add any function of x over here, because that just gets killed over here, right? So I can add anything I want to make this simpler, right? And if I have y squared, I might as well add x squared, right? Now, I have, this is just the distance from the origin, and this is just the distance from the origin. I'm on C. So on C, x squared plus y squared is 1, right? It basically tells you what C is, right? So this thing is actually equal to, because of this C, right? If you did a different curve, then it wouldn't be, right? This becomes 1, so just dx, and this thing is just becomes x, so x dy. All right. So now what we could do is I could plug in the sines and cosines and blah blah blah. But hey, I have a path integral. I might as well just do Greens. So this double integral over d, and now I have my P is 1, my Q is X, right? So it's 1 minus 0, right? dA. So it's just the area of D, which is pi. All right. So it's sort of funky in that there's two places where we applied greens, right? But we didn't just apply green once; we applied it twice. Yeah. But you can apply it as many times as we want, right? It's still true, right? So. So those were a couple of examples. Let's look at one sort of neat application of this before we end for today. It's what if we're looking for the area of D, right? So D is something that C goes around, right? Well, it turns out that we can compute this with well, let me just write it down and we'll see why it's true, right? There's two ways of well, yeah, more than two ways, but I'm gonna first write down two ways. Or the integral over C of x dy, right? Why do these work? Well, by Green's term. This is the P. So this, if you apply Green's term, it just becomes this, right? Because you're gonna have dp dy subtracting dp dy, so I'm gonna have just 1, right? And there is no q, so dq dx is 0, right? Same thing over here, right? So it's the area of D, right? We're just making sure that it is. So Green's term tells us this. Same thing over here. I could take the average of these two, right? So I could take 1/2 C minus y dx plus x dy. That's the same thing, right? It was just average, right? Average of the number with itself, right? Each one of these is useful in some context. So it's actually an interesting application of Green's term, right? I mean, we're computing area by computing some sort of an integral. Now this is so for example, there were these. Well, they still make these devices, these planimeters, which is a device that it used to be that every engineer would have one. Probably a lot of engineers still do. If you need to, compute an area of something, either on a drawing or on a map or something, so you put this device onto the piece of paper. You have to hold someplace fixed, and then you move some arm or something around the paper, around the boundary, right? And then there's a little wheel, and it tells you the area. And they're basically just doing this sort of integration. They're doing it mechanically because integration is just sort of adding something up, right? This is really the integral of a certain vector field. And it's possible to actually do mechanically. Usually, what they have, the old mechanical ones, they have a little wheel, and it's sort of as you move it, if it's slipping sideways, it's not turning. If it's going, if you're moving along the where the wheel turns along that direction, it's turning. So you're doing this integration, right? Just like a car integrates speed to give you distance, right? It's the same thing, except now you're moving in two directions, right? So you can do this integration mechanically and give the area, right? Just by integrating around the boundary, right? So it's there's lots of places where this comes out. Next time, let me not go through that today, but next time show the shoelace formula. It's basically using this idea. and that's sometimes called a surveyor formula. And it's basically you can compute the area of a polygon just by plugging numbers into a table and computing, and it's all due to the Green's theorem. And this is if you're a surveyor, you want to figure out the area of a certain lot, and unless that lot is rectangular, which a lot of times it isn't, well, you plot the points into the map. You read off the coordinates, you plug it into this formula, and you get the area, right? So we'll look at that next time. So.